talk is going to be more developer friendly. I'll be showing a lot of code, so in that sense, it's a little bit different from the older talks. So I hope you like the title. Okay. So if you went to sleep like 5 years back and woke up, you'll find that this works. No, okay. You'll find that people write more code of this style than this style. This is 1.0, this is 2.0 for lack of better name. Okay. Stuff that you're used to, for loops, if then else, you can't find them here. Okay. Used to lists and dictionaries, you don't find this there. But this is more and more systems are written in 2.0 style. They are form the core algorithm part of it. So what are these X's? You have lined them from top to down. What are these X's? So it's a new style of programming. We call it programming with examples and knobs. Don't worry, it's similar to what you have been hearing all day. But at high level, the loop is you have examples, which is X and Y. The black box guesses the output, Y prime, and tries, there's a diff engine, delta, and the diff engine tries to make the guessed output Y prime similar to Y. And if there is a difference, it goes back and turns these knobs so that the next guess Y prime will be close to Y. Okay? So there is this learning loop. These are learning programs that we write using examples X and Y and these knobs, the parameters. That broadly constitutes the majority of code, majority of machine learning efforts that you see around applied to all various fields. It's a new style of programming because you have to get familiar with completely new set of entities here. Okay, there's the annotator, the example generator, stuff you have been hearing about. There's a model generator, model bias creator, model performance improvement engine. Then there's this optimizers which turns the knobs, and then there's this diff engine, the loss function. Each of these entities are verticals in themselves, and surprisingly, a few years back, very few people in the world care about these things. But now, in the 2.0 world, you have to know each of these entities very closely. The common language that these four entities talk through is tensors. Okay? There were lists and dictionaries and sets earlier. Now there are these tensors, these new objects called tensors. Okay, so you have scalars, you have vectors, set of vectors, matrix, set of matrices, three-dimensional array. Start calling them tensors, roughly. Okay, and it could be 4-dimensional, 5-dimensional. You don't need to visualize them. At most, you can view them as these boxes, Rubik cube-like boxes. That's the mental model we keep. Common, all of these, irrespective of working on images, text, sound, tables, all of that has to be boiled down to this tensor format to help this engine, these learning programs work. Okay. So, like sets, like lists, you need to know the API, the programmer interface to this. You have what happens when you insert, what happens when you combine. Tensor also have their own API, and actually a laundry list of APIs. This is just a subset that you see. Reshape, permute, expand, reduce, select, matmul, different kinds of matmul. It's a whole new world. Okay, and anybody who's trying to work with tensors has to get familiar with this API. And then there are these, when you start looking for code that people have written, that you see this kind of weird code which does a reshape of a tensor with a tuple, and there's a transpose with some indices. There are these weird shape modifiers that hijack your code. How do you deal with them? Getting familiar with tensors is really important to write tensor programs, do machine learning programs, deep learning programs. So if you have to sort 2.0, you have to know tensors. So we'll slowly ease into knowing about tensors, and first we get to know them, get to know their flaws, and then we exploit them by making friends with them. So there are two libraries that I quickly talk about that help you work more comfortably or with more ease with tensors. tsalib and Stanley. Okay, understanding tensors, flaws. Good. Let's start with the gory details. The cube that you see in the picture, the sets of matrices, it's actually that's not how it's represented in memory. It's actually a flat list. Okay, and when you request a value for a dimension, there's metadata which is these red and green arrows, which tells you how far do you have to jump into the list to get the particular element. So for the first axis, you have to jump eight elements. For the second axis, you have to jump 4 elements, and you have to work in this flat world if you want to understand the nitty-gritties of how tensors are represented in memory. Okay, there's alternative representation as a matrix. Why is this so? Because if you want to say reorder the dimensions of a tensor, you want to change. Okay, so maybe example I have. So an image is a 4-dimensional or a 3-dimensional tensor where there's a height of the image, there's a width of the image, and then there's channel RGB or RGBA. So that's a 3-dimensional tensor. Text, similarly, word embeddings. You start with string words and have to map them into these tensors. Okay, so periodically you need to permute the dimension, reorder the dimensions of the tensor, make the channel come before the height and width. And this low-level representation actually helps you reorder it without changing the whole memory data layout. Okay, so you can keep the memory layout, but you can just change the axis 0 and axis 1 pointers. And yeah, and actually do the layout. Next time you ask for axis 0, it will jump only four blocks as opposed to 8 blocks. So clearly this representation takes some effort. It's pretty low level, but fortunately, and it's very far away from the high level box view that you have in mind. But unfortunately, the tensor libraries that you work with, starting from the all popular NumPy, TensorFlow, PyTorch, MXNets, all of them are really close to the low level representation. They force you to convert between the box and that flat view all the time. And I'll give you examples. That's why writing these tensor programs, first of all, you have to embed everything all the real objects that you know into these tensors, and then you have to learn to manipulate them. It gets really painful. And the problem is throughout the world, even the Google engineers find it painful. So some examples. Okay. Yeah. So this is an array matrix. You can think of the 2 rows, each with 3 elements. And the library allows you to do a reshape operation, 3-2. It's a valid one because there were 6 elements earlier, and then 6 elements, 3-2 at the end. But you look at the output, you lose the correlation you lose the dimension aspect of it. So 0.1, 0.2, 0.3 are no longer in a single line. They have been jumbled up. Okay, why this happens? It takes a while to think about it and realize that this is perfectly valid if you have the single linear layout in memory, but not semantically. There's no semantic notion of axis or dimensions that the library pretends to give you, but it's not actually there. The library allows you to violate that assumption also. What you want to do here is not reshape, but permute, reorder the dimensions 2, 3, 3, 2. Okay, but now you look at the transpose operator. You have to work with the indices of the dimension. There's no other way. You have to remember that I had this first 0, 1, 2 earlier, and now I have to convert in 0, 2, 1. And if it was 0, 1, 2, 3, you have to careful, permute 1 and 3. It gets painful. Okay. Second thing is about broadcast. So if you basic programming, if you have integer and a float, the integer gets casted into a float and then you can add. That's what happens underneath. Right? So it's casting there. In TensorWorld, it's broadcasting. So you have to add a integer to an array. The integer gets expanded to an array. The top example here. So add integer to an array. Integer gets expanded into array. Maybe in an optimized way, and then you can do the addition. And so you can combine 2-dimensional tensors with 1-dimensional. Everything has to broadcast. Broadcasting is the fundamental underlying primitive of this. Unfortunately, the rules for broadcast at the bottom are ad hoc. They work most of the cases, but they won't work in some tricky or borderline cases. It's like you add in the 1.0 world, you add an element to the list, and you don't know whether it's added to the beginning or at the end. Okay, that sort of confusion. So this This example shows you adding an array of ones of size 32 1 and another array of ones. So the sum should be 64 because there are 32 elements in both of them. But unfortunately, when you do that, it's 2048. The repetitions, the duplications happen 32 times. And why it happens is because the 32 gets broadcast into 1 comma 32, and then it has to match both the two dimensions, and both arrays get broadcast in 32. This follows the rules here, but it's a very tricky thing. And this, when you write loss functions, this kind of errors can crop up and then make your debugging hell. Okay, and finally, the shapes of the tensors, the dimensions, and the values of the size of each dimension. That's the main connect that a programmer has with the library. Okay, so you think in terms of shapes. And unfortunately, there's no way to make those shapes explicit in your code. So this is code from BERT. Okay, how many of you guys know BERT? Okay, some of them. So very crudely, BERT is what BERT happening to NLP is like, A.R. Rahman happening to the Indian music industry. It just revolutionized everything. So this is code from BERT, actual real code. Google engineers wrote it, and you see these names everywhere, different definitions there, and the query layer has this shape B star F N star H. If you remove this adhoc comment and come back even a few days later, there's no way you can figure out that query layer has that shape, and that makes so code without these adhoc comments. So developers need these shapes to be explicit, but all they have is adhoc comments. So, and just builds on that. Essentially, the low-level view of the tensor is exposed at the top, and so you have to work with indices everywhere, and you get weird code like this. So that's, I guess, the best term that describes is tensor misery, a new kind of misery just invented for this talk. So let's look back again at the disconnect. At the top are the images that I showed you earlier. I find it better to view models. Learning about tensors, learning about manipulation is a learning curve for everybody in the beginning. Okay, it's better to view them as just trees, partitions. So if you have the first dimension has 2 partitions, you have 2 outgoing arrows from the tree. Then next dimension has 2 more arrows. Finally, you have 4. Okay, and if you go down, you find a scalar value at the bottom if you pick each dimension. A more compressed representation is on the right. Just have a ordered dimensions, and the size of each dimension is mentioned. A more closer to semantic view is when you label them, you give them names. So it's B, T, D, batch, time or length, and the embedding dimension. Okay, so that's if you give them names, it automatically becomes easier to think about them. Okay, the last one is the real conceptual view where these dimensions are not related. That's also useful. So unfortunately, we think our mental models are at the right end, and the memory represented at the low end, and programmers have to constantly convert between them. Okay, so we know tensors now briefly, and we know some of their flaws, and now we are ready to befriend them or exploit those flaws to help them work with us. Key idea is very simple, just to name the dimensions. And even though so instead of referring them by indices, you call them BTD or NCHW. But we have been using that, but those are not integral part of these libraries. And a lot of people have realized that naming these dimensions, that libraries should have inherent name dimensions. And there have been proposals since 2017, Google, Facebook, a more recent post by Alexander Rush. But all of these proposals are involve changes which are deep into the libraries. These tensor libraries are really complex. They have, besides these operations, they have auto differentiation implemented in there, and nobody wants to touch that without having clear understanding. So making deep changes is out of the block, except very recently, last month, I think, PyTorch added a named dimension support on an experimental basis. The TensorFlow, people have built libraries on top to add names. Almost everybody knows that it's important, but nobody has a very clear way to do it. Okay. Meanwhile, this project started, I started writing some code decoder for sort of Indian language translation, Indic language translation. And I took some code somewhere, and this is the forward loop of the the decoder, and it's almost impossible to modify this code without knowing that. You have to add like dozen of print statements everywhere to figure out what the shape are. It's impossible without making them explicit. So we decided what can we do about it, and that led to this library. So our goals are don't make deep changes to the libraries. Um, that's their work if they want to do it very well. We still want to have the names around. Once you have the names, you want them as first-class citizens, not as ad hoc comments. And we want to write crisp transformations over them. That's interesting that I'll show. Also want to write assertions over them. Many of the bugs that a beginning programmer faces is about shape violations. I put in the right shape. Why is it failing at the middle of my network? Okay, so we want to write assertions, just like in 1.0. Assertions are extremely helpful and essential. And work with arbitrary backends and integrated Python. It should work right now, as opposed to waiting for a proposal to be implemented. Okay, so quick example. Yeah, this is the RESTnet. How many people know RESTnet? It's the core block of vision networks. And this is the forward function on the left. You can scroll on, it's very easy to read. If you want to understand what shape changes are going on here, you have to go and read the layer 1 function, which is make layer, and you can try to decipher that piece of code. The tsalib version is this. Okay, the same forward function where each variable is labeled by its shape. So what you see are x colon something, which is the type annotation that Python allows. You can put arbitrary types or your own defined types there. And we chose a particular language to define this top. At the top, the starting point is how to define, it's like the database schema. We define the name dimensions in a structured way at the top and use it throughout the program. So irrespective of whether these networks are complex question answering networks or multi-layered faster RCNN, the number of dimensions that involved are actually very few. And that's a very important observation. We can just declare them one place and use them throughout. And suddenly your program becomes much more readable. You start with an image, which is batch and 3HW. And the number of channels increases 64. The height and width decrease by 2. Again, the height and width decrease by 4. You can see the flow of how shape changes until it becomes a flattened array to be classified at the bottom. Okay. There's one drawback here, that these are global variables. So you can further implement, plus it's a little bit busy here. You can reduce the clutter by just putting these strings with special language where you specify these shape expressions. Okay, these are arithmetic, not just names, but also arithmetic expression. And you can do stuff like get the integer value of the dimension by name and use that in functions as integer values. So that helps the program be clean, and you can track the shapes everywhere. You have to write these annotations manually, but once you write them, this is a module used by everybody. Everybody can build upon it, use it. Okay, more examples. There's the dot product. If you have looked at sum representation, it forces you to write all the dimensions. Instead, we have these underscores, which help you get rid of the unwarranted, unneeded operations, unneeded dimensions in this operation, and just expose the dimensions on which the tensor product happens or the matrix multiplication happens. Align to is an explicit broadcast. If you remember the 32-1 example, the library had no way to know that the 32 at the bottom and the 32 at the bottom were aligned. They are aligned in some way. So having the names, just saying that this is BD and that is BLD, so automatically when you expand, you insert a dimension in between and not anywhere else. That helps explicit broadcasting. So we introduce a bunch of operators here which allow you to write shape transformation in a clean way and with name dimensions. And all of this works with TensorFlow or PyTorch or whatever library, because there's a very small adapter, backend dependent adapter that you need to change. Okay, and you can write these shape assertions, which are, instead of writing the numbers 224, 3, and so on, you just write the symbolic names or expressions, which you can directly, match. If you even change those defined values, these assertions, your program doesn't change. That's the advantage of using names in assertion. Okay, much fun. So we started with, this is a hairy slide. If you want to make, mathematicians do this to make your slides complex. But basic idea is that you start with just dimension names, but you need expressions. You saw that, height divided by 2. You need expressions also. You need a language or grammar to define them. Okay, so that's your symbols, constants, arithmetic operators. You can have even list of these shapes. List of shapes get compressed into a single tensor. That's an operation that a lot of these networks do. Okay, once you have this language, you can look at the bottom. A permutation is just BTD going to DTB, as simple as that. A stacking operation is BTD star, a sequence of these BTD tensors going to a B and a new dimension inserted there, and TD. Simply all of the laundry list that I show you is very simply expressible if you choose to have these dimension names. And so in fact, you can just forget what was there on the right hand side, those the names of the APIs, which is very hard to learn. You just forget them and just use this notation in your programs. So that is what we did, and this is an example from GPT-2. This actual code lying out there at the Hugging Face repository. Okay, this is the old function at the top, which is beautifully cryptic, and we introduced this warp operator, which allows you to do sequence of transformations in the named world. Okay, so all that function is doing is to convert tensor of BHTD shape to BTHD and BTH star D. It's wonderful to spell out these things. Okay, but it is just extremely explicit. That's what that's what this complicated function was doing, and this is actually a very simple representative, more readable, concise code that does that. So advantages. So we actually, to see the advantages of this name represent, because nobody had written code using name stuff. We took BERT, okay, and we tried to rewrite as much parts of it to incorporate these named dimensions. And what we found, the many such big functions actually just translate to one-liners. That's all that's going on. And it's awful, it's painful, it's misery to write it like that and not like that. So having a sequence of transformations actually just helps you a lot. And we actually managed to cut down 25 lines of one of the main functions. It's just illustration that, this is a code that has been stable for a long time, but it could be made much more concise and more readable to do that. Okay. So I told you about a sort of grammar names, a grammar over those names that can be used to specify shape transformations. But what is going on underneath? Essentially, you have to, the libraries still understand 0, 1, 2, 3 indices, and you're working with names, so you need a way to lower these names to the library integers. And so, I mean, we use the machinery of symbolic expressions, a library called SymPy, which allows us to, for example, if you have this shape expression, you give them the indices, B goes 0, T1, D2, K3, and then evaluate the right-hand side in this context, 0, 1, 2, 3. And you automatically get that 2, 1, 0, 3 sequence, you pass it to the low-level library. That's how the low-level, the lowering happens. Okay, I mean, I'm just jumping over it quickly if you want to know more details. And right-hand side is what, again, mathematicians do to make it more cryptic. Okay, and all of this in open source. So this is tsalib library. I think it has been developed majorly in the beginning of this year, and a lot of people noticing it. Users growing a little bit, not as much as I'd like to, and yeah, people like it. And I'd like to know if you are working with tensors, if you are working with these ugly programs, I suggest that you try tsalib, and feedback welcome. Contributions also welcome. Okay, so picture abhi baki. There are still two issues. You have to still write these manually, annotations manually, and you have to still write the named assertions explicitly. So that gives rise to the next tool, which now builds upon tsalib, and it's a dynamic shape checking tool. So again, some code. If you have the function foo, where you have y and z that you obtained by doing a mean of x along different dimensions. So you have to use 0 and 1, and using 0 is an error. So you did an aggregation along the 0 dimension, which was wrong. Aggregation along 1 dimension was needed. So this is an error that nobody will flag. Your program will run through, and at a later stage you'll just crash, and you won't know the problem is right here. And so we track shapes but we need assertions there. So the idea is to use these labels as implicit assertions. And when you have these assertions, the tool can run and just point out the error. So at line 36, it's good. That's the shape you specified, and that's the shape of the actual runtime value. Line that you expected BD, but in fact it's TD. So the runtime gives you an error. And line 38, that succeeds. So you can use this. If you write them, you automatically can check them. And if your program changes, you make inadvertent errors, you can the tool tsanley can help you. Yeah, the internals I can talk to you if you are. It basically builds on the Python tracing mechanism and piggybacks onto it and does some AST parsing and all that. Okay, so tsalib and tsanley are at Off-Note Labs. One of our big goals is to do open source research, and right now the focus is to build tools which help developers write machine learning programs faster and quicker and simpler. And these two tools are. We are also building this tool LiteX. Some of the talks mentioned or the discussion mentioned the problem of experimenting. Machine learning, deep learning is primarily an empirical science. There are a huge number of experiments that you have to do to figure out which of the options are correct, irrespective of how much intuition you have. A lot of it is art right now. So experimenting is better. People have not paid as much attention to how experimentation framework should be designed, and LiteX is an effort. Other projects that we plan are building data pipelines, which is another. This was more about modeling this complex. We want to make writing pipelines also much simpler as compared to state of art. And for the final thing is debugging the hardest problem. And well, we want to solve it. Not sure how. Okay, so that is basically the talk. I told you about what tensors, what they look like, and what the semantics are, what the problems are, what the flaws are. And these two libraries will help you befriend tensors, essentially bridge the disconnect between the low-level model that the current libraries have and your mental model. And naming has multiple benefits. We hope TensorFlow and NumPy in particular adds these name dimensions internally, so everybody benefits. But until then, you have tsalib. And coming soon, you have taming tensors. It's not just befriending, we need to actually tame them.